Our speaker today is Romyar Sharifi from UCLA. Romyar is an expert in US Hava theory. We'll talk about some connection between arithmetic and topology.
Okay, I'm very happy to be here. Yeah, so I wanted to motivate this talk with a question I don't really think about, but so let's let R be a commutative ring. And then the question is, what are the solutions to x plus y equals 1 with x and y units in this ring? So they're invertible. So as a special case, if we're doing number theory, you might consider, well, for instance, you might consider z adjoin 1 over n, right? So this would be a ring of n units, of n integers, and the units would be called n units. So you're allowing n to appear in the numerator or the denominator. Maybe more generally, let me give you an example of this first. Okay, so an example, you could think of this as, you're inverting a certain number of primes, right? You're allowing certain numbers of primes to appear in the denominator. So if you just had one prime, right, z1 over p, there are solutions if and only if, let's say, p equals 2. Okay, units where you only have p in the denominator. So p in the numerator and denominator. So what are the solutions? They're 2 plus minus 1 is minus 1 plus 2 is 1/2 plus 1/2. And all of those equal 1, right? I only allow 2. Maybe, so what if you had 2 primes? So this is, it was Min-Young Kim who told me this. So let's say I have z1 over p not equal to q prime. So this has solutions if and only if a pq is even, okay, meaning one of them is 2. And so in this case, we have z1 over 2p, p's odd, let's say, p odd. And then, well, no, solutions require pq is even. Well, no, I guess there are solutions if and only if pq is even. Yeah. All right. Yeah. Let me try to avoid that. Yeah. Okay. So there's solutions. So of course we always have those solutions, but so there's new solutions if and only if p is Mersenne or Fermat prime. Okay, so this is a fun exercise, right? What are the solutions? What are some solutions in that case? If say 2 to the n plus or minus 1 was a prime, right? Then I can do this. Yeah. If this is a prime, right? I now have the numerator and denominator only involve 2 in that prime, and that's the only way you can do this. Okay. More generally, you might consider the case of a number field. That means a finite extension of Q. It has a ring of integers, and you have something slightly larger. If I have S as a set of prime ideals of its integer ring, I could sort of allow only S in the numerator and the denominator. So one way to say this is that outside of S, so for the integer ring, I allow only S in the denominator. So this would be like A and K cross, such that let's say A equals B over C. Let's say its integer ring is OK. B and C in OK. So A can be written like this. where, let's see, C is not in P for all P not in S. Okay. So that's the exact analog or extension of this. And so the solutions are called, well, the equation x plus y equals 1 with solutions in this ring, equation x plus y equals 1, xy in OKS cross is called the S unit equation. And back in 1929, more general theorem, in fact, but Siegel proved that there are only finitely many solutions for a given K and S. So there exist only finitely many solutions for a given K and S to the S unit equation in K. Okay, let me give you just a slightly different way to think about solutions. So if I look at the set of XY pairs in R cross, R is my ring, x plus y equals 1, I claim, so you can make sense of the projective line over any ring, even over Z. And let me say that solutions here are in one-to-one correspondence with solutions with points on P1 minus 0, 1, and infinity are points. So what does this mean? Okay, so P1, right, if I subtract out infinity, just becomes the affine line A1, so it's the plane. Now I'm removing 0 and 1. So you can think of points on the plane as corresponding to maximal ideals in a certain ring, but maybe P1 minus 0, 1, infinity. If you like, this can also be thought of as GM minus 1, the multiplicative group, so I remove 0. But this is, if you don't know what this is, I'm going to tell you different correspondence. Okay, so this is spec of Z. I do this over Z. Z, x, 1 over x, 1 minus x. I've removed 0, and I've removed 1. And so solutions so points correspond to ring homomorphisms from this ring, Z, x, 1 over x, 1 over x minus 1, or 1 minus x, to R. Okay, so you might just say solutions to the S unit equation are in correspondence with ring homomorphisms. How? Well, I maybe shouldn't have called it X. So if I have a solution x comma y, let me call this x goes to the solution x. Okay, right? So I have a variable here. I can send it to whatever I want, right? As long as both it remains invertible here and 1 minus it is invertible. Okay, so that's the requirement. That means that both x and 1 minus x have to be a unit. So the image is exactly the S units. Okay, so you could try classifying all ring homomorphisms. I'm not going to do this, but this is actually why Mignon would be interested. Okay, so, but it's through this correspondence that Siegel was able to prove this theorem. Okay, another thing you could do, let's say you knew all solutions to the S unit equation, then you could describe the following group. So this group is called Milnor. It's a Milnor K2 of the ring. It's not something that's very much studied unless the ring is a field, but we can make a definition. So we take the units, we take the tensor product over Z, thought multiplicatively with the units. Okay, so it's like look at formal sums of pairs of units, and then I'm going to mod out by all the group generated by Z linear, all x tensor 1 minus x's, where x and 1 minus x are both units. Okay, so if I had all solutions, I could compute this group. Oh, here I should have said finite. Right, it's very important. Okay, maybe an exercise here. In this group, x tensor minus x for x in R cross has trivial image. Okay. So this is related to a more usual group called, there's an actual K2. There's an algebraic K2. K2 of R. And there's a map from Milnor K2 to the actual K2, where the image of a, the class of a tensor product here in the quotient is set to a symbol often denoted the same thing in Milnor K2, but called a Steinberg symbol. So this is a sort of a group, sort of a much studied group. And it's sort of the product in K theory. There's a theorem that in fact for R field, 1969, that this map Milnor K2 to K2 is an isomorphism. So for R field. In general, for a general ring, it can be very far from being an isomorphism. It can be neither injective nor surjective. For S integers, K2 is much better understood than Milnor K2. This group K2OKS is a finite group. You can determine it. I mean, there's sort of an explicit description of it in terms of K2, of the field, of the quotient field. Yeah, it's really unclear. I mean, in fact, its order is known as well. But it's unclear what this group is, right, for OKS. So my interest has been mostly in cyclotomic fields, and in particular, the ring of integers of the, let me just take a p-th cyclotomic field. The ring of p integers of the p-th cyclotomic field. So here p is an odd prime, let's say. And mu p is the p-th roots of unity. So I join all p-th roots of unity, and I invert p. So what relations can we find in Milnor K2 of this ring? So one nice thing about this ring is that, well, there's a nice subgroup of units, which has finite index in all the units. It's very easy to write down. So let me take zeta p to be a primitive p-th root of unity. I set inside C, so here's one, right? Primitive p-th root of unity. And I can consider so there's a group C inside Z mu n 1 over n cross of cyclotomic p units. And what are they? They're generated by 1 minus zeta p to the I. You could take all I, or I could take I between, say, 1 and p minus 1 over 2, because you get almost the same thing up to 2 p-th root of unity, because you also have the 2 p-th roots of unity in the field Q mu p. Okay, so yeah, so this is the group of cyclotomic p units. In fact, its index inside the full group is what I'll call H plus. It's the order of the class group of the maximal of a field of index 2 in Q mu p, called the maximal totally real subfield. This is what you get. It's the sort of fixed field under complex conjugation. right? The zeta p plus zeta p inverse is fixed by complex conjugation. This is a degree p minus 1/2 extension of Q. And this sort of class number is, so this is the group of ideals class group, right? It's ideals mod principal ideals in the ring of integers. And it sort of measures the failure of unique factorization or to be a PID of this ring Z mu p 1/p. So, okay, so what was I saying about these particular, the fact that you have these cyclotomic units, I mean, they give you like lots of solutions to the unit equation. Maybe you've noticed some already, I don't know, but here's one. Zeta p to the a plus, more than 1 minus zeta p to the a equals 1, right, for all a. Yeah, so so maybe a slightly more interesting family. We could do 1 minus zeta p to the, let me use u because later I'll use, I'm using the, later I'll use u. So 1 minus zeta p to the u over 1 minus zeta p to the u minus v plus 1 minus zeta p to the v over, this is maybe not the simplest way to write it, but it avoids having another root of unity here somewhere. 1 minus zeta p to the v minus u equals 1 for all u and v. Of course, v should not be u. And uv should not be 0 mod p, not be divisible by p. So you have lots and lots of solutions. In fact, there's a book, I just borrowed it the other day in preparation by Bombieri and someone's, okay. But anyway, they point out that these are sort of all the non-real solutions to the unit equation in this ring without inverting p. These are actual units. Okay, but if you go to real units, there's they point out that they do some computations and mention in a remark that there's a lot more. So let me list a lot more in a second. But first, I'm allowing p units, so I can quickly get some more. Let me quickly get some more. Plus, plus, plus. Okay. I think this still ends up adding to 1. Now this is a unit, this is a unit, this is a unit, but this is a p unit, so it's not sums of 2 actual units. Okay, so here's a question: with so many relations, could this map at least be injective, or could the map K2, for this ring Z mu p 1/p Milnor to K2 Z mu p, this also has a lot of generators, be an isomorphism? And I don't know the answer, but I'll talk more about it. Okay, one reason why this might be interesting, you might say this is a rather strange group, this K2 to consider, or this Milnor K2. I haven't even really said what K2 is, but maybe I could just quickly relate it to something more familiar in this particular case. So there's a theorem, very special case of the theorem due to Tate in 1976, that if I take K2 of, let's say, Z mu p 1/p, and now I tensor it with FP, so I reduce it mod p, then this group is the same as the class group of Q mu p. As a group, it's the same as tensored with FP, but I can also, this has a Galois action, actually, for the Galois group of Q mu p over Q. And this will become a Galois, I can put mu p, which is the group of p roots of unity, that has a Galois action. And this becomes a sort of respecting Galois actions. Isomorphism respecting Galois mu p over Q actions. So in fact, this K2, at least mod p, is your usual class group. So something of, quite a classical interest. I'll mention, I think now more, yeah, wait. So why is it of classical interest? Let me back up a bit. Okay. So so let me go back. Kummer, sort of 1850. Right? If P doesn't, so we have, if P doesn't divide the class number of Q mu P, not the totally real subfield, but the class number of Q mu P, then x to the P plus y to the P equals z to the P has no solutions in positive integers. So the question of whether, this sort of group mod P, what is this group with mod P at least? I mean, is this even true on P, on P parts, assuming this group here is finite on the left? Sort of related to this question. He also proved another theorem in 1852. So primes such that P does not divide H, like in this theorem, are called regular primes. And otherwise called irregular. The smallest three irregular primes, I'll write them down in a second, are 37, 59, and 67. It's an open question of whether there are infinitely many regular primes, although it's known there are infinitely many irregular primes. But as you'll note, in density, there seem to be more regular primes than irregular primes, and one can give a precise number. So here's another theorem, maybe more relevant for what we're doing. Kummer, I think 1852. P divides H if and only if P divides one of the numerators of one of the Bernoulli numbers B2, B4, BP minus 3. And none of those have P in the denominator. So I mean, divides the numerator. So BK equals the kth Bernoulli number, which is given by the expansion of x. It's the kth derivative of x over e to the x minus 1 at 0. In other words, if I write it like the Taylor expansion, I have bk here at some rational number over k factorial, and then x to the k. That's the kth Bernoulli number. It's almost an even function. So other than b1, the odd Bernoulli numbers vanish. Bernoulli numbers for odd k. So, okay, so if P divides BK, we say that P comma K is an irregular pair. And the smallest three irregular pairs, or at least primes, the smallest K is 12, divides 691. But so PK regular pair, if P divides BK, so the smallest three primes I said were 37, which divides the 32nd Bernoulli number, 59, which divides the 44th Bernoulli number, and 67, which divides the 58th Bernoulli number. You could ask, how many, well, okay, maybe we could ask a different question. You could ask, what does the divisibility of a single Bernoulli number by P tell you, right? And it tells you about some piece of the CeLO P subgroup of this class group being non-trivial. So here I'll get, okay, just to be a little technical, right? Delta was the Galois group of Q mu P over Q. It's completely determined by what it does to a p-th root of unity. So in other words, if I have delta, I can look at what it does to a p-th root of unity. And it's going to have to send it to another primitive p-th root of unity, some power. And that power only matters mod p because this is a p-th root of unity. And so we can declare it to be like omega of delta. And this gives you a homomorphism from delta to fp, which is an isomorphism. And so if I have a module, let's say it's exponent p, fp delta module. So that means that delta acts, and it's also an FP vector space, and the actions commute. then it breaks up as a direct sum of sort of eigenspaces for the different characters. I mean, this is a group of cyclic group of order p-1, so there's a generator, and you could just look at like eigenvectors for that generator. And so maybe I equals 0 to p-2 ai, where ai is the set of a in A, such that if I have an element and I act on by A, it acts by the ith power of this character, right? So just, yeah, okay, for all delta or for the generator. So which piece does p k being irregular tell you about? So theorem, in one direction, this is due to Herbrand in 1932, and the other direction due to Ribbit in 1976. And I just learned last night that Ribbit just won the Steele Prize for this particular paper. Okay, so and that says that P divides BK if and only if I take the class group, I reduce it mod P. Okay. Oh, yeah. If and only if this 1 minus kth or p minus kth, let me write it as p minus kth, so is non-zero. So it's the p minus kth. I hope that's clear. Can you read the p minus kth? Yeah. The p minus kth eigenspace of this thing is non-zero if and only if p divides this kth Bernoulli number. And this is sort of the first instance of something that's a theme in my research that I may have time to say a little bit about later, but I mean, he used the Galois representation attached to some cusp form. So this is basically the constant term of some Eisenstein series, and this Eisenstein series. So if I look at it mod p, it looks like a cusp form, and he somehow used a Galois representation attached to this cusp form to construct some element of this class group, if you like. Okay. Yeah, I know there's topology in the title, but we'll get to it maybe. Okay, so Kummer actually, I don't have the year written down, but Kummer proved that remember I had this plus part of the class number. Okay, the plus part actually divides the whole class number. If p divides the plus part, then it divides actually the rest of the class number as well, the minus part, which is like h over the plus part. So really, you might be complaining that k is always even here, right? Like I'm talking about k even between 2 and p-3. So this is odd. So I'm only dealing with odd eigenspaces. What about all the rest? Well, if one of those happens to be non-zero, then already some minus eigenspace will be non-zero. And in fact, the Kummer-Van der Waals conjecture, so it was popular. It was called Van der Waals conjecture for a while, but he lived much after Kummer, and Kummer had sort of studied it. And that's p does not divide h plus. Okay, and this is known for. It may not be true, but it's known for p less than 2.1 billion, or 2 to the 31st power, more precisely, by Hart, Harvey, and Ong, who did some other calculations, maybe 2017. Okay, so you'll be looking for a while if you want to find a counterexample. Okay, so now a question that arises is how many Bernoulli numbers does p divide? Okay, we could call that the index of irregularity. IP equals number of k between 2 and p-3 even. Yeah, p-1 you might ask about, but actually p divides the denominator, and that eigenspace of the class group is always trivial. Okay, so such that p divides bk, the index of irregularity. So actually, slightly expanding upon, or considerably expanding upon Kummer's result. Yeah, so okay, so they actually computed the index of irregularity. So for all of these primes, yeah, IP is less than or equal to 9 for p less than 2 to the 31. Okay, so it's quite small, at least computationally. If you could just show that it was less than the square root of p minus square root of p minus 2. So Eichler 1968, 65, and Bruckner 1975. Really, this is Bruckner's result, but similar thing was proved by Eichler. If IP is less than square root of p minus 2, then x to the p plus y to the p equals z to the p has no integer solutions with p not dividing x, y, z, what's called the first case of Fermat's last theorem. So if you could just show it's that small, you would already have much of Fermat's last theorem. And you notice, I mean, this is a lot smaller than the square root of 2 to the 31, right? But how do you show that? Okay, so, right. Okay, so now let me get back to this question of K2 Milnor and K2. Because remember, I said K2 is related to the class group, right? K2 is the class group mod P. Okay, so I could look at the pairing, right? Like C tensor C. This is going to surject onto like your Milnor K2 of your ring of integers, P integers. Even mod P, of course. Do I want to do it mod P? Yeah, let's do mod P. And so it will map. This maps to K2 of the actual K2. Oh, I should say of who? McCallum and myself, 2003. And remember that this was the same as the class group. I think I want to take, actually, I need to do something. I need to take the part fixed by complex conjugation in this group, just to be technically correct. So that corresponds to the, I should be, yeah. So if I write FP here instead of mu P, this is the minus part. So it's the odd eigenspaces that we were talking about, the ones that are, whose non-triviality is determined by these Bernoulli numbers. So the minus part is the sum of the odd over odd I, and the plus part's the sum over even I. And okay, so what's the conjecture? That this map, this one here, right, is surjective. Right? So the Steinberg symbols, C is the cyclotomic P units, right? Or so you could just say Milnor K2 surjects onto K2. But in theory, this could be slightly bigger than this if the P divided, if Van der Waals conjecture failed. Otherwise, I mean, this is always bigger, but my point is like this could have more units, right? Like this ring could have more units, mod P, if Van der Waals conjecture failed. Because remember, the index of the cyclotomic units in the full group of units was the plus part of the class number. So P will divide that index if and only if Van der Waals conjecture, Kummer-Van der Waals conjecture fails. So, but for the purposes of small p, you might think of this this group as being this group mod all x tensor 1 minus x is, or x 1 minus x or c.
So we don't know unconditionally that the vertical map is subjective?
Oh yeah, we don't. So let me not write that. Yes.
Okay.
Yeah. So in other words, Steinberg symbols of cyclotomic p units generate K2. That's the conjecture, the plus part. I'm not including Van der Waals conjecture in the conjecture. So if I did, the minus part would be 0. Yeah.
The composition of the two horizontal maps kind of explicit.
This composition?
Yeah.
Yeah, sure. It's AB goes to the class group.
Yeah.
No, not so explicit. K2 in class group is not that explicit. Yeah. But yeah. Okay. So okay. so we did some computations. So you can take the relations I've already written, which are now erased, but all the ones I already wrote, okay, right, in among cyclotomic p units, even when I changed it to plus. Okay, just take exactly those relations and mod out C tensor C by those relations, right? What group do you get? And well, what we computed is that for every irregular pair pk with p less than 25,000, so which eigenspace? So I said p minus kth eigenspace. So for the class group, it's the p plus 1 minus kth eigenspace, or the 2 minus kth. So I will just say like this: C tensor C mod, the set of X tensor 1 minus X's, right? This group, and then we take the 2 minus kth eigenspace. That corresponds to the 1 minus kth eigenspace of the class group. I need mod P. So mod P, tensor FP, has FP dimension 1. It shouldn't have FP dimension 0 because I'm supposed to get K2. And K2 exactly in those eigenspaces is one-dimensional in all of these cases. So what I'm saying is that the Milnor K2 mod P is at least as big as FP for every single one of those irregular pairs. But there could be more relations. So it could be a bigger group. It could be a smaller group. Okay, but it certainly gave us the impetus to make this conjecture. So here's a question. Is this an isomorphism, right? I said this earlier, is Milnor K2 tensor FP in this case the same as Milnor's K2, regular K2 tensor FP? And I'll say not clear, because there are some regular eigenspaces where P doesn't divide the kth Bernoulli number, where all the relations I listed and all the relations I know don't make this 0. And it should make that 0 because the K2 is, the class group's trivial in those eigenspaces, right? So for instance, if 2 and 3 are squares mod P, which is 1 mod 4, then the 2 minus kth eigenspace for P comma P plus 3 over 2 is bigger than expected when I mod out by all known relations. It's one dimension too big. So let me mention I want to go back to the fun stuff I was doing at the beginning. What are all known relations? Let me write down, this is where I probably should switch to slides, but let me write down some relations. Okay. Well, first, let me point out that, zeta p, I had this one, right? And you may have observed that this is just a family coming from like x plus 1 minus x equals 1, right? Yeah, in the cyclotomic units. Yeah. But now it actually comes from something in a polynomial ring, is my point here, right? Like these are units in the ring Z, x, 1 over x, 1 over 1 minus x, right? Which remember was the spectrum of this is GM minus 1. The multiplicative group minus 1. 1 is from here. Okay, I removed the point where x is 1. Yeah, and more generally, I had this other relation that looked like x to the a minus 1, x to the, okay, I wrote it in terms of u and v, but, right, I had something like this. And now, well, this looks like, actually, this gives me something in z, x, 1 over x, and now 1 over x to the n minus 1 for all n greater than or equal to 1. right? Which you can think of, now I'm removing all roots of unity. So this corresponds to like GM minus all roots of unity, okay? So one can ask, like, what is Milnor K2 of this ring? Or if you like, you could notice that A and B are really two different variables, right? So I could write x, y minus 1 plus y minus 1. Oh, sorry, x, y inverse. But you can fix it so that they're all polynomials, right? I should have written it as pluses. X to the minus a, y to the b, minus 1. And so equals, oh, so no b. Yeah, like that, right? Equals 1. So this is the ring, like, what is it? This is like GM squared minus all, one way to do it is rank 1 tori. So, right, all GMs in GM squared. So I removed x equals y in particular. So maybe, in particular, in this case, I removed x equals 1, y equals 1, and x equals y. So how far can you go with this? So back in 2004, I wrote a computer program. Try to find all solutions. Mm-hmm. Yeah. Right. Yes, that's right. Yeah. Yes, that's right. Yeah. And so z mu p1 over p here. Yeah. So some others. Okay, let me just written as, I'm going to write them as a. You might notice this could also be written as a plus b equals c if I multiply the denominators to the other side, right? So what are some other solutions? So here's one: x y squared plus y plus 1 plus x minus 1. Oh, I'm writing in the x squared. I'll write lower and equals x squared y plus xy plus 1. Hopefully I translated them right. X squared plus 1 squared plus x minus 1, x y squared minus 1 equals xy plus 1 squared. X y cubed. I mean, this is the entire list essentially, so might as well write it down. Where? Oh, yeah, plus. Thank you. Yeah. 4. Okay, now I can get 3 variables. I mean, of course you could homogenize. You can always sort of add in infinitely many variables. But okay, and this is maybe the last one. I eliminated 2 variables. I had it with 6 variables, but let me just write it with 4. X, y, u minus 1, z minus u plus u, x minus y, z, x minus y equals xu minus yz, x minus yu. Okay, those are all the ones my computer could find back then. And notice the last one. If I plug in roots of unity and I divide both sides, I have 2, root of unity minus another root of unity here, right? And 2 here and 2 here. So when I divide, I'm going to get actual units because like zeta p to some power minus 1 over zeta p to some other power minus 1 is an actual unit in z mu p. So these are sums of 2 units in the z mu p, not with p inverted equaling 1. And so I was mentioning that in this book of Bombieri, they had done a computer search to find as many solutions as they could find. Maybe they found all of them. Here's a question: do these give you all of them? These plus this, right? Plus those. I don't know. I never thought about it before this talk, but so. Of course, that would be a hard question to answer if you can't even say whether the cyclotomic units are all the units, right? But okay, and actually back then I made a conjecture in a talk I gave in 2004, only on the slides in that talk. Yeah.
Those have some geometric interpretation.
I mean, they're on different GM to the n minus rank n minus 1 tori, right? Like, so they're all coming from relations in Milnor K2 of some ring of many polynomials where I'm inverting like, you know, things like this equals this, right? I'm removing things like the plane where x equals, think of it as a plane. I mean, it's multiplicative, but x equals yz. Yeah.
And you conjecture that in GM to the n minus tori, these are the only families?
I don't want to make that. I mean, I don't know how. Yeah, yeah. It's a question, right? Are there others? Yeah. What's the maximum number of? Notice some of these. Oh, I think I left one out. Oh yeah, no, here. No, I definitely left one out. Yeah, there's one other. There's one other that has more terms, I think. But right, like how many? What's the? Is there a maximum? There should be a maximum to the number of terms you can have in any one of these expressions. And yeah, what is the maximum, right? Like, I guess the way I've written it here, you have to define what term is, because if you write it differently, there might be a lot more. But here, I don't have more than 2 terms in any of yeah. Okay. Ignoring the powers of x and things. Okay. So my conjecture was, you'll notice that there's something going on with 2, the cyclotomic polynomial for 4th roots of unity, the 4th cyclotomic polynomial, the well, okay, that's not the 3rd cyclotomic polynomial, right? But no, you're not seeing any 5th cyclotomic polynomial there. And so I conjectured there does not exist an f in z x 1 over x, 1 over x to the n minus 1, n greater than or equal to 1, g in z x 1 over x, 1 over x to n minus 1, where 6 does not divide n, and such that f of 1 equals 0, g is not a power of x, and f plus g equals 1, which would eliminate things like 5th cyclotomic polynomials from appearing. Why would this matter? So now let me, in the final minutes, say something about homology of modular curves. Okay, so you have the complex upper half plane, and you can extend it by adding in the points in P1 of Q. So you add in the rational numbers and Q infinity here. And this is the complex upper half plane extended. And it's acted on by, well, SL2R, but I mean, in particular, it's acted on by a subgroup of SL2Z called gamma 1 of P. And this is the A, B, C, D in SL2Z, such that P divides C, and D is congruent to 1 mod P. And P divides D minus 1. It's a subgroup. And we can take the quotient. So the action is via Mobius transformations, right? A, B, C, D. Z is A, Z plus B over CZ plus D. We can take the quotient space, and that's the closed modular curve. It's closed because I threw in the cusps, which are the images of P1 of Q under this quotient. So X1 of P is the quotient of H star via this action. It contains the cusps. Let me call them C1 of P, which are gamma 1 P, P1. Okay. And I can consider the homology of this curve relative to the cusps. H1 of the curve relative to cusps. I'm going to take it with FP coefficients because why not? So it's generated by modular symbols, which are classes of paths between the cusps. So if I want to think of this as on the upper half space, if I have, let's say alpha beta in P1Q, I have an alpha here and a beta here, and I can draw a semicircle here, the geodesic, or I might have a gamma here. And so this is like alpha beta, and this is gamma goes to infinity. Because the H is sort of simply connected, these generate this relative homology group. Okay, but this is an infinite set of generators. It's way too big, right? There is a finite set of generators. It actually has an explicit presentation. To connect it to what we're doing, I want to consider a slightly smaller group. So let me consider the subgroup. How do I say it? Let's see, C0 is the group of cusps, which are classes of cusps of the form I over P. I is between 1 and P minus 1. There's actually, and I guess over 2 is enough, but okay. That's like half the cusps. And I also want to take the part, I want to take the real part fixed by complex conjugation. But what is complex conjugation here? The upper half plane is not fixed under complex conjugation. It's the part fixed by z goes to minus z bar. Okay, so in the resulting group, take some of the cusps. So I'm only considering paths between those cusps. And then I just sort of symmetrize everything by taking a modular symbol, adding its complex conjugate, which is just like corresponds to negative alpha, negative beta, and then dividing by 2. It's generated by symbols UV. This is monin. Maybe 72 or 73. Forget which year. UV, where U and V are in FP and non-zero. So what is the symbol? UV is the class of the path from B over D to A over C, where A, B, C, D are integers such that AD minus BC equals 1. And U is congruent to C mod P. V is congruent to D mod P. They're the reductions of C and D mod P. You can always find such a thing. And then there are relations. And the relations here are this. UV is the same as minus UV, because I'm on the plus part. Same as minus VU, which is the same as U minus V, UV minus U plus U minus V. This might look familiar. I guess I'm going to erase this. Okay, I only have like a minute left, but okay, so and let's just let UV equals 0 if U or V is 0. We'll allow that. So Buzyok and I defined a map in 2007 from the homology to Milnor K2, or to usual K2, Z mu P, 1 over P, tensor FP, plus part, sending a symbol UV to 1 minus zeta P to the U, 1 minus zeta P to the V. And now why is this well defined? Because you'll notice that the relation among cyclotomic units, which I wrote down twice, 1 minus zeta P over U, 1 minus zeta P to the U over 1 minus zeta P to the U minus V, plus 1 minus zeta P to the V over 1 minus zeta P to the V minus U. If you write that out, That gives you 4 terms, one of which is 0, and the 3 remaining terms correspond to uv equals uv minus u plus u minus vb. So the fact that this is a well-defined map actually just follows from the Steinberg relations I've already written down. But this map has a lot stronger properties. So theorem, in this case, due to Fukai and Kato, just published, but let me write 2012 when they actually put out a preprint. That this map is called pi. Pi is Eisenstein. And what does that mean? There are Hecke operators, so I'm out of time, so let me just say that you have Hecke operators Tn, n greater than or equal to 1, and there's acting on this homology group. And if I compose pi with this Tn, I get exactly this. What I would get if I apply pi to, which you can see what it is, pi to n times uv plus nu nv. So this is for all n greater than or equal to 1, taking this to be 0 when it needs to be 0. So this is telling you then something about relations in Milnor K2, perhaps. And for n equaling 2, so there's an explicit recipe due to Morel for what this Tn of uv is. If you want, I'll write down a couple examples. And for 2 and 3, we could prove this explicitly. Buziok and I already did that. Because the relations come exactly from some of the relations I just erased. Okay, but for n, say at least 5, none of those relations give us this. So why? I don't know. But so one could ask, are these relations in K2 that don't come from Milnor K2? Or are they somehow seen in Milnor K2, but not in an obvious way as from simple tensors? So I'll leave it at that. Right, thanks.
Okay, thank you very much for that questions.
The index of regularity, is there some reason why it is so called? Is there something useful about having high index of regularity?
Well, having low index of irregularity would be useful for the reason of proving the case of Fermat's last theorem. I guess it was just interesting, what is the what is the how many Bernoulli numbers does it divide? That tells you how many of these eigenspaces of the class group are non-trivial. Right, the odd ones. It's exactly that number. I mean, another useful thing is the FP dimension of the class group mod P, right, which is very much related, because usually these eigenspaces, these odd ones, if they're non-trivial, they're cyclic. Under Van der Waals conjecture, they're all cyclic. And I should say, actually, the index of irregularity is equal if instead of the plus part of this, so the FP dimension, if I take this, no, not this. I mod out by all these sort of relations coming from Eisenstein series. I take the minus part instead of the plus part. So this group mod Eisenstein ideal, its FP dimension is the index of irregularity. Yeah.
More questions? Yes.
At some point early in your talk, you said something about the index of the circular units, canonic units inside the full group of units.
Right.
So that was exactly the cardinality of the class group. The real subfield.
Yes.
So that kind of struck me. Is that really true on the nose?
Yeah, I think it's true on the nose for P prime. No, the whole thing is, I think. I think that's, I think it's true for primes. Otherwise, there is an annoying power of 2 that occurs when you're divisible by multiple primes. Yeah, for prime powers, I think it's exactly on the nose.
It said.
Yeah, it's computing. Yeah. I mean, there's various criteria for a pair to be irregular in terms of sums of powers, mod P, and things like that. And so they introduce fast Fourier algorithm, things I don't know. But yeah.
By actually calculating.
No, not directly. Oh, one thing I didn't have time to say is that so through another result of Fukaya-Kato from the same year, this map, right, is surjective in particular for p less than 2 to the 31st power, which implies my conjecture with McCallum for such primes. Okay. Yeah.
More questions? In Zoom, maybe?
Oh, maybe.
Oh, yeah.
This conjecture that is there on the top left.
Right.
So it's not exactly the same, but it's similar to Zegel's theorem for other rings, right? You're not even asking them to be units, but it's kind of.
Oh, no, that's a typo. That's a typo.
So, okay.
Yeah.
Just trying to think
Right.
about the question. So it's really asking for a sharp, more extreme version of Zegel's theorem, but for other rings, right?
Yeah, yeah.
So, okay, so is there a wider philosophy when Zegel's theorem should hold? Suppose you ask just that there are finitely many such F and G, not that there are.
Right, right. I mean, finitely many might be hard because, well, you could see that the way I wrote it, when I had an A and B in the exponent, right, there were an A and B in the exponent, and A and B vary. So that's infinitely many already if I'm not like working with roots of unity, right? Like X, there's infinitely many powers of X. But yeah, families, yeah, you could be asking for finitely many families in a sense, right?
If the unit group is finally generated as a C modular.
Yeah, I think that's a general theorem, right? Yeah,
That's a
when you have in fact, Carlo was telling me that last night. Yeah. So, yeah. Yeah.
I just have a very quick question. You mentioned in Kate's theorem that K2 is essentially clustered. So can one use this one, for example, to calculate Iwasawa invariance?
Well, you could if you can get a handle on K2. So if you had, for instance, that the Milnor K2 was the same as the K2, then yeah, in theory, but Iwasawa invariance, yeah, it's probably not the best way to do it, right? Like, it's like K2 is pretty complicated. I don't know if it's more complicated, but yeah, it's pretty as complicated, at least I would say. Yeah. Yeah.
Same as regular K2. What can you gain?
Well, that's a good question. I mean, what can you gain? I mean, I guess you're describing then the K2 in some sort of explicit fashion, right? But there's not, yeah. Like I said, I don't know. It's not a much studied object, right? So probably studied by me. Yeah, right. But yeah, so I don't know what you get exactly from Milnor K2 as K2. I think you get a lot more from like homology being K2, right? Yeah, because then you're connecting something in topology. And really this like homology Mod-Eisenstein ideal, which mod these relations is something very explicit, which in theory you can compute by a fairly simple recipe. And so that would be giving you a recipe over here. Yeah.
More questions? If not, let's